Hello everyone. In this lecture, we will look at an encryption primitive called a block cipher, which can be used to encrypt and decrypt data using a secret key. If you recall, in the first lecture, we looked at another encryption primitive called a stream cipher. So both stream and block ciphers can be used to encrypt data using a specific secret key. However, as you will see, they are quite different in their construction and security assumptions. But let's begin. So the block cipher. This is how a block cipher looks. It is a function that takes plaintext and the key and returns ciphertext, which is produced by encrypting the plaintext using the key. In this lecture, we will not study how it works internally, but what it does is that it permutes the bits in the plaintext using the key. The block cipher, as its name implies, works on blocks of data. The block size is usually 16 bytes, so it takes a 16-byte plaintext and returns a 16-byte ciphertext. The key here can be of different lengths. It does not have to match the size of the block. Usually the key is 16 bytes, providing a 128-bit security level for encryption. To decrypt the data, we have to use a different function, a decryption function. It is very similar internally. What it does is that it performs operations in the reverse order. Here we cannot take the ciphertext, encrypt it once more to get the plaintext, as it was in the one-time pad crypto system. If we were to encrypt the ciphertext once more, we would get a double encrypted plaintext. Okay? So what are the properties of this function? The first property is that it is deterministic. It means that the same key and the same plaintext will always provide the same ciphertext, so there is no randomness used in the process. An essential security property here is that without the key, the plaintext cannot be found. Now, but what about brute force attacks? Can the attacker brute force the key? Well, this depends on the specific block cipher that is used. However, usually if the size of the key and the plaintext is the same, it means that there will be a unique key for every plaintext, and the attacker will not be able to figure out which key and the plaintext is the correct one. So encryption of a single plaintext under a key of the same length may provide unbreakable security, similarly as in the one-time pad crypto system. However, if more than one plaintext is encrypted using the same key, the attacker in the brute force process will be able to detect the correct plaintext and key. For example, the attacker will be able to conclude that the correct key is the key where all blocks decrypted with the key carry some valid, meaningful plaintext, right? Another important security property is that valid plaintext ciphertext pairs do not leak the key. For example, if you know the plaintext and corresponding ciphertext, it does not really help you to speed up the brute forcing of the key. What it does, however, is that it gives you a reference point to detect when the correct key has been found. Then the diffusion and confusion. This property is important to guarantee security of the block cipher. What it basically means is that if we change just a single bit in the plaintext and apply encryption with the same key, the ciphertext should re-randomize. Similarly as for hash functions, half of the bits in the random positions in the ciphertext will flip. The same applies also to the key. If only a single bit is changed in the key, the whole ciphertext changes. Essentially, it means that similar plaintexts or keys must not produce similar ciphertext. If this property did not hold, it would be possible to use the ciphertext to learn something about the key or the plaintext. The most popular block cipher used today is AES, which stands for Advanced Encryption Standard, which was standardized by NIST in 2001. AES has a 16-byte, 128-bit block size and supports three key sizes, 128, 192, and 256 bits. The length of the key here corresponds to the security level provided by the key, because in a brute force attack, the attacker would have to try all permutations of the key to find the correct one. Now, as you see, the block cipher itself is quite a simple and secure primitive. However, the problem is that in real life, we usually want to encrypt something larger than just 16 bytes of data. We want to encrypt gigabytes of data. So how do we do that? A very straightforward idea is to simply split the data into 16-byte chunks and encrypt them separately. The recipient will also decrypt them separately and join the plaintext together to recover the original data. The methods used to encrypt data larger than the block size are called modes of operation. The most straightforward mode of operation is called electronic codebook or ECB mode. Now, the problem with this mode is that it has a serious security issue. The problem is that since this process is fully deterministic, the same plaintext blocks will encrypt to the same ciphertext blocks. So if the attacker sees that this ciphertext block matches this ciphertext block here, he can conclude that these two plaintexts are also the same. Okay, but so what? How does knowing that these two plaintext blocks are the same could help an attacker in practice? So this is where we have to look at this famous penguin image. Let's assume that this is one big bitmap image and we have encrypted it using this ECB mode. Here's how it will look encrypted. As you see, here are some quite visible patterns. The reason why we see these patterns is because the pixel blocks with the same color were encrypted to the same ciphertext value. This white background here produces one ciphertext value and these black pixels another. As a result, this allows us to clearly identify the image that was encrypted. You would agree that this is quite a serious fail for an encryption scheme. And this is a very good example which shows a common problem in cryptography and when building security systems in general. How independently secure building blocks, when combined together, do not actually achieve the security we expect them to provide. Anyhow, so how do we fix this problem here? As you can see, the root of the problem here is that there is no randomness introduced in the encryption process. The same plaintext value encrypted with the same key will always produce the same ciphertext. A simple idea is to add random padding to every plaintext. For example, let's use the actual plaintext for half of the plaintext block and the other half we set to some random data. After the decryption, the recipient will simply discard the second half of the decrypted plaintext, and this way, even if the plaintext prefix here and here is the same, because of the random padding, the ciphertexts will always be different. Nice idea, right? Let me introduce the idea of the initialization vector, or IV. The idea here is very similar. On encryption, we XOR the plaintext with some random data called IV. Since this IV is random, by XORing the plaintext with IV, we get another random data. This guarantees that the input to the encryption function here will be random in all cases, even if the plaintext values here and here are the same. Now, for the recipient to recover the original plaintext, we have to send this IV along with the ciphertext to the recipient. IV does not have to be secret. It is just a random value. Knowing the IV does not help an attacker learn anything about the plaintext. We can safely send it together with the ciphertext. On decryption, the recipient has to XOR the decrypted value with the IV to get back the original plaintext. So on encryption, we flip the bits of the plaintext, and hence on decryption, we have to flip them back to recover the original plaintext. Very nice. The problem. The problem is that the ciphertext is now 2 times larger than the plaintext, because for each ciphertext block, we also have to send the recipient the corresponding random IV value, which is not good. By looking at this scheme for a while, we should come to the idea that by doing one simple hack, we can remove the need to send these other IVs to the recipient. We only need to send the first IV. How is it so? Well, the requirement is that the IV has to be random to produce different ciphertexts for the same plaintext. Instead of generating a random value, why not to use the ciphertext of the previous block as a random value for the current block? We know that due to the properties of block cipher, the ciphertext will have the same properties of random data. So we can use the ciphertext as an IV to encrypt the next block, the next ciphertext to encrypt the next block, and so on. And this is where we come to the CBC or Cipher Block Chaining mode. Here's how it looks. Here we need to only send an extra 16-byte IV for the first block. For the other blocks, the ciphertext from the previous block is used as an IV. And what we see is that it provides the security. After encrypting the image using the CBC mode, we don't see any patterns anymore. Now, what happens if you use a fixed IV or no IV at all here? What will be the security implications? Well, if we encrypt the same file twice, it will result in the same ciphertext. But what if we encrypt two different files, but the prefixes, beginning of these files is the same? In this case, the ciphertext blocks will be the same until the first block where the plaintext blocks are different. All other ciphertext blocks will be different regardless of whether the ciphertext corresponding plaintexts are the same or not. So even if our random IV is not that random, it is not that critical and still much better than using the ECB mode where every plaintext block was encrypted independently. So this CBC mode, which you see here, is the most popular block cipher mode of operation that is used in practice. There are some limitations, however. Serial encryption. In CBC mode, we have to encrypt data consecutively, right? We cannot encrypt this plaintext block before this block has been encrypted because we are using this ciphertext block as an IV to encrypt this block, and so on. This means that if we want to speed up the encryption using parallel computation, we cannot do it easily. However, we can perform parallel decryption here. We can decrypt this ciphertext before the previous has been decrypted. What we have to do is to decrypt the ciphertext and take the ciphertext from the previous block to recover the original block here. So for decryption, we can use several CPUs to speed up the decryption process. What about integrity or malleability? What happens to the plaintext if an attacker modifies a single bit in the ciphertext? Remember, in one-time pad and stream ciphers, the same bit would be flipped in the decrypted plaintext. But what happens here? What happens if we modify, let's say, the first bit here in the first ciphertext block? When decrypted, will we get the same plaintext here? Or the plaintext with a single bit flipped here? Remember, even a single bit change in the key or ciphertext at decryption will completely randomize the plaintext. So this plaintext block here will be random garbage even if just a single bit is changed somewhere here. Okay? Now, what about this second plaintext here? As you see, the decryption of this block uses the modified ciphertext of the previous block as an IV to recover the plaintext. How will this plaintext change if we change the first bit here? Exactly, because of the XOR operation, the corresponding bit will be flipped here. So basically, if you modify the ciphertext, the current plaintext block will be all garbage, but the next plaintext will be flipped in the same positions. Does it influence the next blocks? For example, this last plaintext block here. This will be garbage. This will be flipped in the corresponding position. But what about this plaintext? Will it stay intact? Yes, it will stay intact because this last ciphertext was not modified, and this previous ciphertext used as an IV for decryption of this plaintext is also not modified. So we will get the original plaintext here. Now, can such malleability attacks be exploited in practice? Yes, they can. Even though the modified ciphertext produced a garbage plaintext block, the modifications can be used to precisely influence the following plaintext block in a meaningful way, which may lead to successful attacks. Therefore, remember once more, encryption does not provide integrity. What we can do here is that to provide integrity for the encrypted data, we can calculate the message authentication code over the ciphertext so that we could verify that the ciphertext has not been modified by third parties. Now, as you see, the block cipher works on the specific size of data, usually 16-byte blocks. What if the length of our data is shorter and does not fill up the full block size? Well, in that case, we have to pad the plaintext. And there are several ways to pad the plaintext. One way is to pad it with random padding, and another is to pad it with zero padding. However, in both cases, this makes it hard to determine from the padding how many padding bytes were added as padding. Yes, we could tell the recipient how many padding bytes we added, but that's an additional data field to transmit. A good idea is to specify in the padding how many padding bytes were added. For instance, ANSI padding scheme specifies it in the last byte, the other padding bytes being 0 bytes. Then this ISO padding scheme fills other padding bytes with random bytes. And in this ISO padding scheme, the padding length is not encoded in the padding, but the recipient can detect where the padding starts, as the padding starts with 80 in hex and then 0 bytes. If you look at this padding in binary, we will see that the most significant bit is 1, and then all the remaining bits are zeros. PKCS padding is what we commonly use in cryptography. In each padding byte, we specify how many padding bytes were added. If we add 3 padding bytes, we specify value 3 in each byte. If 5, then the value 5, and so on. What is important to note is that padding must be added even if the plaintext occupies a full block. Yes, this means that in such cases, we have to encrypt an extra block, a block full of padding bytes. However, if this extra block was not added, in such cases, we would not be able to determine if padding was added at all. For example, we would see this value, but we would not know whether these bytes should be interpreted as padding or they are part of the actual plaintext value. Therefore, we have to always add padding. A mode of operation you also should be aware of is the so-called CTR or counter mode. This mode uses a block cipher as a pseudo-random number generator to produce a key stream for a stream cipher. Here is the idea. What we do here is we encrypt some counter value or sequence number which we increase for each following block. Since the input block for each encryption is unique, we will also get out a unique random ciphertext. This ciphertext is used as a key stream to XOR it with the actual plaintext that we want to encrypt. On decryption, the same process is repeated, but here we pass the ciphertext and get back the plaintext. So here we are using a block cipher to build a pseudo-random number generator. As you remember from the previous lecture, we could also build a pseudo-random number generator by using a hash function. Once we have a pseudo-random number generator, we can turn it into a stream cipher as you see here. However, we have to remember that the nonce must never be reused. So the same stream cipher requirement applies here as well. We have to guarantee that for the same key, this input is always unique. Otherwise, the same key stream will be reused and it will be possible to attack the plaintext, right? So this is a good place to discuss which is better for use, a block cipher or stream cipher. Security and performance-wise, they can both provide the same security level and a similar performance. So where are the differences? So first, we know that we have to use a stream cipher when we need bit-by-bit encryption, when we must be able to send out part of the encrypted plaintext as soon as possible. In some cases, we cannot afford to wait until the whole plaintext block is filled up to encrypt it using a block cipher. So basically, if we need to encrypt real-time data, such as voice, we would have to use a stream cipher. Another benefit of stream ciphers or block ciphers in CBC mode is that it allows us to encrypt and decrypt data blocks separately. We can take the ciphertext block we want to decrypt, encrypt the corresponding counter value, XOR the output with the ciphertext, and get back the plaintext. Now, if we are building a security system where we don't need bit by bit or parallel encryption, I would recommend staying away from this counter mode and stream ciphers in general, because it is much harder to implement stream ciphers securely. In particular, the requirement for stream ciphers that the same nonce is never reused. Yes, also in case of block cipher in CBC mode, we have to ensure that the IV is random. But if we fail and the IV turns out not to be random, then it is not a tragedy, as an attacker can only learn that the same data or data with the same prefix was encrypted. However, in the case of a stream cipher, the reuse of a nonce can be used to figure out the key stream and in the worst case lead to the recovery of the plaintext, which is a much worse security issue. Therefore, when designing crypto systems, we have to also consider the implementation aspects, answering the question which one can be implemented securely easier, which relies on less security assumptions or weaker assumptions to ensure security. Okay? Okay. Another mode of operation which has recently gained popularity is GCM or Galois counter mode. It is the so-called authenticated encryption mode. Here is how it works. It is essentially the same counter mode as you saw on the previous slide, but in addition it also calculates a message authentication code for all ciphertext blocks. So as a result of encryption, we get the ciphertext plus an authentication tag. When decrypting, we will recalculate the tag, and if our recalculated tag does not match the received tag, then the decryption fails. The authentication tag is usually 16 bytes long, providing 128 bits of security for integrity protection. The name of the mode has Galois here because this function uses Galois field multiplication, whatever it is, to calculate the authentication code here. Please note that this here is a simplified illustration because the MAC key here is actually not the same as this encryption key here. The MAC key is obtained by encrypting with the encryption key the nonce that is used here. This way, the authentication tag also authenticates the nonce. Also here, what is not shown is that it authenticates the length of the ciphertext as well. Okay. The GCM mode is standardized for block ciphers that have 16-byte block size, where nonce is the first 12 bytes and counter the remaining 4 bytes. Now, since the counter is only 4 bytes long, it means that after encrypting 4 billion blocks or 64 gigabytes of data, the counter will repeat, right? So in case that happens, the same key stream will be produced, which will enable attacks on plaintext and also enable to trivially recover the derived MAC key that is used here. So this counter mode should not be used to encrypt more than 64 gigabytes of data using the same key and nonce. Okay? The GCM mode provides what is called authenticated encryption with associated data. The associated data means that optionally in the GCM mode we can authenticate some additional data that needs to be authenticated but is not encrypted. In such cases, we would add that additional data here before the first ciphertext block is fed to the Galois hash function. Now, this GCM mode is really nothing special. We could achieve the same features using HMAC here, just that this mode has been standardized to provide authenticated encryption in a single scheme and also claims to have some performance benefits. Alright, I hope that now you have an idea of how we can use a block cipher to encrypt files, but let's look now at the disk encryption use case. So, the disk encryption use case. First of all, I hope that all of you are using full disk encryption on your laptops. If not, consider using it. For instance, in Ubuntu, full disk encryption can be easily enabled when installing the operating system. There are 3 clicks to be made. Advanced features, use LVM, and encrypt the new Ubuntu installation for security. And then it will ask to configure the encryption password, and after installation, each time when booting the operating system, it will ask for the password to be entered to fully boot the operating system. The idea of full disk encryption is that the whole root partition is encrypted. Only the boot partition is not, because to boot the system, the software code that asks for a password and unlocks the encrypted partition cannot be encrypted, right? An alternative is to use file-based or container-based encryption for sensitive data, but it is much less secure because when you work with the decrypted plaintext data, the copies of the plaintext may end up in the temporary folders on the unencrypted hard disk partition. Also, the file names, which on its own can carry sensitive information, are listed in the operating system activity history and can leak through other means. Therefore, full disk encryption, where the operating system partition is also encrypted, is the correct way to handle sensitive data. Anyhow, so how is the disk encrypted? Here is how data on a hard disk is addressed. Historically, hard disks were physically and logically split into tracks and sectors, where sectors used to contain 512 bytes. The sector was the smallest addressable unit. If you wanted to read or write a single byte on a hard disk, the operating system had to ask the hard disk to read or update the whole sector. Now back to our disk encryption question. Can we encrypt the whole disk using CBC mode? We know that we can easily encrypt files using the CBC mode of operation, but can we encrypt the whole disk using the CBC mode? The problem in this context is that in order to, for example, decrypt this sector here, we would have to retrieve the last ciphertext block from the previous sector, since the previous ciphertext block is used as an IV for the first block in this sector. So if we need to decrypt one sector, we would need to physically read two sectors, which is not good. A much bigger problem is that if we wanted to change a single block in the middle of the disk, we would need to re-encrypt the remaining blocks, because encryption of the current block depends on the encryption of all the previous blocks. Not good at all. So when using CBC mode for disk encryption, each sector is encrypted separately. If we need to modify a sector, we re-encrypt the whole sector. Not a problem, because to read or write any byte in the sector, we have to read or write the whole sector anyway. The question, however, is where to store the initialization vector. These are an extra 16 bytes per sector. If we did not use an initialization vector, then the sectors containing the same data would contain the same ciphertext values. For example, an attacker could detect empty parts of the disk where it is all zeros. To solve this problem, we use the sector number as the initialization vector. Not a perfect solution, because the IV in this case is not random, but at least it is unique, guaranteeing that the same plaintext sectors will encrypt to different ciphertext values, because IV will be different. Very good. Now, how do we provide integrity of the data? MAC is not an option, because we don't want to recalculate the MAC on the entire disk if something is changed somewhere. We could do it per sector, but where do we store the 16 extra bytes of MAC for each sector? The truth is that today's disk encryption solutions do not provide integrity of the encrypted data. What it can provide is that if someone modifies a single bit of an encrypted sector, after decryption, the corresponding block of the sector results in random garbage. This is the best we can do to prevent meaningful malleability attacks. This is done using the so-called XTS mode of operation, where encryption of each block in the sector depends not only on the sector, but also on its position in the sector. This prevents an attacker from moving ciphertext blocks around without damaging the corresponding plaintext. Please note that regardless of that, the attacker can always take a snapshot image of the encrypted disk and restore it back later. It will boot fine, nothing will be corrupted, but you will be booting an outdated version of your computer, which can be a problem if this outdated version has remotely exploitable vulnerabilities, for example. On the other hand, if an attacker has physical access to the encrypted computer, then it may be easier for the attacker to simply backdoor the code in the boot partition that asks for the password. The next question is, how can we change the encryption password without the need to re-encrypt the whole disk? If someone shoulder surfs our password, we really don't want to reinstall our computer or re-encrypt the entire disk to change the password. The solution here is to use a concept called master key. So when we set up full disk encryption, a random master key generated which is used to encrypt the data. The master key never changes. To change it, we would need to re-encrypt all the data. Now the password that we as users enter is used to encrypt the master key. This encryption of the master key is stored in the disk header. So you see, when we enter our password, it is not directly used to decrypt the data, but to decrypt the master key, which is stored encrypted in the disk header. So to change our password, we would have to take the encrypted master key, decrypt it with our current password, re-encrypt it with our new password, and store the new encryption of the master key in the disk header. I hope that is clear. Enterprise solutions usually have several encryptions of the master key. This allows several unique passwords to be used to unlock the encrypted value. This is very useful in the corporate setting so that administrators could access the encrypted disk without asking the users for their password. Now, whenever we are discussing disk or file encryption, we are usually talking about password-based encryption, right? However, at the end of the day, that password somehow has to be converted to an encryption key of specific size so that it could be passed to the cipher. The core question here is how to derive strong 128-bit key from short, low entropy passwords. Let's say a user enters a 10-byte password. How do we use it as an AES key? Because AES will not accept a 10-byte key. It needs exactly 16 bytes for the key. So what can we do? Well, we can simply pad the password with 60 bytes and use it as a key. We can do that and it will work. But what if the password is longer than 16 bytes? By truncating the password to 16 bytes, we would discard the extra entropy contained in the password. So here we can use all the same ideas which we used for storing password hashes in the database. First, we use a hash of the password. This way, we stretch or compress the entropy contained in the user's password over the entire key, over the entire 16 bytes. If the output of the hash function is larger than 16 bytes, what we need for the key, we can use the first 16 bytes of the hash value as the key, and this should not reduce the security. So, by hashing, we will distribute the entropy over all 128 bits. Very good. Then we can use a salt as an addition to the password. So we don't use the password directly, but we concatenate a salt to the password before hashing it to derive an encryption key. How will it help us? As you remember from the password hashing, it will prevent multi-target attacks, requiring the brute forcing of each password separately. The last thing we can do, we can use an iterated hash to slow down the brute force attack. This will add an arbitrary number of operations to each brute force try. But that is basically it. We cannot do any better. To obtain the full 128-bit security level provided by the encryption function, the user would be required to enter 16 random byte values. This is not something a user can remember and type in easily. Therefore, at the end of the day, the password-based encryption schemes will not be able to provide the maximal theoretical security level of 128 bits as provided by the crypto primitive. The attacker is clever. Why brute force all possible 128-bit keys if it is possible to go an easier route and brute force our low entropy password, right? So this you have to take into account whenever assessing the security of any password-based encryption solution. There is a standard function that can be used to derive keys from passwords called password-based key derivation function 2. The 2 is here because the function 1 had some limitations on the length of the key it could derive. This function does not have such length limitations. So this function accepts 5 parameters: pref, password, salt, iterations, and key length. pref is the pseudorandom function to use. As its underlying pseudorandom function, it uses an HMAC construction and not a hash function directly. Password is the password entered by the user. Salt is a random value recommended to be at least 64 bits, 8 bytes long. Iter is the number of iterations desired, and it is recommended to be at least 1,000 iterations, and this will increase the security level by 10 bits. NIST recommends 10 million for critical keys. This increases the security level by 23 bits. I can tell you that on my computer it takes around 10 seconds to derive such a key. But I can probably wait 10 extra seconds when booting my computer or when opening an encrypted file container. Now, for instance, Ubuntu disk encryption selects iteration count that corresponds to 1 second. So when configuring the disk encryption, the performance of your computer is measured and an iteration count that corresponds to 1 second on your computer is chosen. So it means that after entering the password, your computer will hang only for a second. But this also means that the slower your computer is, the less secure encryption you will get, right? Keylen is the desired length of the key to be derived. This is in bytes. The length here is not limited. Basically, this function works as a pseudorandom number generator and is able to generate as many bytes as needed. This password-based key derivation function is used in quite a few popular standards. For example, WPA2 Wi-Fi protocol uses password-based key derivation function to derive encryption keys from the password that we use to authenticate the wireless access point. An interesting observation here is that the name of the access point, SSID here, is used as a salt. This means that an attacker can build a lookup table for the most popular access point names and brute force passwords for them in parallel. From this, we can derive good security advice, namely to set up wireless access points using a unique access point name to prevent cracking our password using pre-computed lookup tables, right? As you see here, WPA2 uses 4,000 iterations, which increases the security level by 12 bits. Another interesting note is that the once popular encryption tool TrueCrypt uses password-based key derivation function with iteration count 2000, which is a relatively low iteration count. So the advice here is, before deciding on what password-based encryption solution to use, it might be useful to first find out the default iteration count that it uses and whether it is possible to increase it. So this password-based key derivation function 2 is quite popular, but for new schemes, the script or argon2id functions are recommended for key derivation. By the way, the latest version of Ubuntu has switched from this password-based key derivation function to this argon2id function for disk encryption. The reason is because these both functions are memory intensive and therefore cannot be optimized using special purpose hardware, as we discussed in the previous lecture. Very good. Now, the topic of the homework task is password-based file encryption. The task is to implement a utility that encrypts and decrypts files using a password. Let's name the utility AES.py, and it works in two modes, encrypt and decrypt. When executed using the encrypt option, the first thing the utility will do is to benchmark the performance of the computer to see how many iterations the computer can perform in 1 second. So on my computer, it can perform around 800,000 iterations in 1 second. And this number then must be used as the iteration count to derive the encryption key. Then the utility asks for a password, derives the keys, and encrypts the file. The decryption mode will ask for the password, derive keys, decrypt the ciphertext, and write the plaintext to this file. The integrity of the ciphertext here is provided using HMAC. So the key derived from the password will be used not only for encryption, but also to provide the integrity of the ciphertext using hash-based message authentication code. The parameters for key derivation, encryption, and HMAC are ASN1 dir encoded and stored as a header of the ciphertext file. So if we dump ASN1 the ciphertext file, we will see that it starts with a dir encoded data structure, and then some data follows, which is the actual ciphertext. This is the description of the ASL1 structure. So here is a sequence that stores 3 subsequences inside it. So here are the key duration function parameters, salt, iteration count, and key length. This is cipher info that stores encryption algorithm AES CBC, and here the initialization vector. And this is the HMAC info using the digest infrastructure we saw in the previous lecture. It stores here the hash function used in HMAC, SHA-256 in this case, and MAC digest here. The test cases. We create some plaintext, encrypt it using some password, decrypt it using the same password, and we should get back the original plaintext. Another test case where the plaintext is exactly 16 bytes to test if the padding is correctly handled. Then trying to decrypt with a wrong password. We see the MAC check failed. And decryption of a big file to verify that our code handles everything correctly. So this big.enc file is available in the course repository. We have to use this specific password to decrypt this file. And here it shows the AES and HMAC key, which you can use for debugging to verify that your code derives the keys correctly. In the case of a successful decryption of this file, the SHA-256 hash of the plaintext should have this specific value. The requirements and instructions for this homework. Slow down brute force attacks to 1 try per second. Of course, assuming that the attacker uses your computer for brute forcing. Benchmark the time required for 10,000 iterations, and then extrapolate the iteration count to 1 second. Here is an example in Python of how to measure the execution time of some code here. Use password-based key duration function with HMAC SHA-1 to derive 48 bytes. This is how you will call the password-based key duration function in your code, and it will return you 48 bytes of key material. Now, when benchmarking, make sure to use realistic parameters here. A password of a decent length, salt of 8 bytes, and key length 48 here, because the speed of the key duration function depends on these parameters. We want to use the same or very close parameters as we will use when deriving the actual keys. Now, of the derived 48 bytes, we will use the first 16 bytes as an AES key for encryption, and the remaining 32 bytes as an HMAC key for MAC calculation. We are using 16 bytes here because 128-bit AES requires a 128-bit key, and 32 bytes here because SHA-256 has a 256-bit 32-byte output size. This way we get the best security out from HMAC. Here it does not matter much because both these keys are derived from a password, which most likely will have lower entropy than these keys. But of course, we don't want these keys to have a lower entropy than the password, as in that case, the attacker will not brute force the password, but these keys. So why are we using 2 separate keys here? This is because when designing crypto systems, it is a good practice to use separate keys for separate purposes. In this particular case, it probably will not create a security issue, but in general, it is much easier to prove the security of a scheme if the same key is not reused. Therefore, to be on the safe side and to make security analysis easier, let's just use different keys for different purposes. We can afford that. Using a key duration function, we can use the password to generate as much key material as needed. Okay? Okay. Then generate 16-byte initialization vector and 8-byte salt randomly using osurandom method as in the first homework. The requirement for this homework is to implement CBC mode of operation using the pure AES, so-called ECB mode of operation. The crypto library provides AES in CBC mode where all the chaining is done for you, but here our purpose is to learn CBC mode. Therefore, you have to implement the chaining yourself. This is how you will use AES functionality in your code. You will initialize the AES cipher using a key, XOR plaintext with the IV and encrypt the result, On the decryption, you will do it in the opposite order, decrypt the ciphertext and XOR it with the IV to recover the original plaintext. Use PKCS5 padding, where each padding byte encodes the padding length. And make sure that padding is always applied, even if the length of the plaintext is already a multiple of 16. Now, a few more notes. Do not overcomplicate the task too much. The entire plaintext and ciphertext can be stored and processed in memory. The CBC mode of operation you have to implement working on 16-byte blocks, so this will still require the use of a loop. A few notes about MAC calculation. First, it is important to calculate the MAC on the ciphers text and not the plaintext. Yes, we could instead MAC the plaintext and it would work, but this should be avoided. The reason is because to verify the integrity, we would then need to first decrypt a potentially modified ciphertext. In general, if possible, it is better to avoid processing and parsing potentially malicious input, as the attacker can construct it in a way to exploit our system, or by observing how our system handles the input, deduce some secrets or even the secret encryption key used by our system. More about this on the next slide. The second requirement is to prepend the initialization vector to the ciphertext when calculating the MAC. This is important to prevent an attacker from modifying the initialization vector. The initialization vector has to be authenticated because the result of the decryption depends not only on the ciphertext, but also on the initialization vector which we use to decrypt the ciphertext, right? So this is one way we can implicitly authenticate it. Finally, use the HMAC compare digest method to compare the calculated MAC with the MAC from the DER-encoded header. I will explain why in the next slide. So that's it for the homework task. Now, the last topic we have to discuss in this lecture is side-channel attacks. Side-channel attacks are a very important class of attacks which are quite frequently neglected in cryptography and cybersecurity in general. Let me give an example. Let's say we are auditing some web application and there is some admin authentication function that compares the password received over the network with the actual admin password that is hard-coded in the code. Consider, for instance, this Python code. It receives the password, which is emitted over the network, and compares whether the submitted password matches the hard-coded password, in this case QWERTY. If it matches, it returns code 1, access granted. Otherwise, it returns 0, access denied. If we, as auditors, look at this code, there is really nothing wrong with it. There are no flaws. It compares the submitted password and returns the correct return code. However, surprise, surprise, this function is vulnerable to a side-channel attack, or more specifically, to a timing attack. And the reason here is that this string comparison operation here is not constant time. The comparison stops after encountering the first incorrect byte. And it makes sense. If the first character of these strings is not the same, we can tell that the strings are different without checking the remaining characters, right? Now, let's assume that we are running this code on a very slow computer, such that, let's say, one CPU instruction executes in 1 millisecond. Now, if we send the password AAAAA and measure how fast the access denied message is returned, we will obtain 1 millisecond. If we send the password PAAAAA, we will get the same 1 millisecond. However, if we send the password QAAAA, where the first character matches the first character of the hard-coded password, the response time will be 2 milliseconds, because this string comparison operation will have to do an extra step, verify the second character, therefore taking an extra millisecond. And so on. If the first 2 characters are guessed correctly, we see 3 milliseconds. If the first 3 characters are guessed correctly, we see 4 milliseconds. 4 characters, 5 milliseconds, and so on. Effectively, this allows the attacker to brute force character by character, which is much faster than brute forcing the entire password at a time. Now, is this attack exploitable in real life? It turns out that it depends on how precise the timing information the attacker can obtain. Research has shown that these type of attacks are exploitable over low latency networks. For example, a local network, or even better, if the attacker is running their measurements on the same machine where the vulnerable code runs. Over high latency networks such as Wi-Fi, this would be much harder because the network would introduce delays, making the measurements imprecise. So how can we protect against this attack? One idea would be to put a sleep call here for a random amount of seconds before returning the access denied message. This way, these two measurements would provide different timing, right? However, introducing a random delay before the return will actually not solve the problem completely, because this random delay can be cancelled out by collecting more measurements. So, by collecting the average over measurements, the attacker will be able to distinguish between these two distributions, the average in this case being slightly higher. Yes, it would require more trials from the attacker, hence the attacker would be slower, but the flaw would not be completely eliminated. To solve it completely, we need a constant time string comparison function, which does not stop when encountering the first incorrect byte, but continues checking all the other bytes and then provides the final result. This Python string comparison is not constant time operation, and as a rule, in other programming languages, it is also not constant time, because using constant time string comparison is not efficient and is only needed in very rare cases when sensitive data is compared against untrusted data. So, as a general rule, whenever our code handles some secret data, such as passwords and keys, the code should use constant time operations to make sure that no information about the secret values leak through timing. The problem is that in practice it is very hard to write constant time code, because in order to do that, you have to know how the compiler works and sometimes even how the specific processor executes the code. For example, in the case of C language, the compilers are pretty smart to optimize inefficient code. So the compiler can conclude that the constant time code is stupid and may simply optimize it away, replace it with an insecure but more efficient string comparison algorithm. So it is not trivial at all. So instead of trying to fix this ourselves, in practice we should, as much as possible, use crypto implementations provided by decent cryptographic libraries. The most popular libraries have pretty good support against these side channel attacks. If there are some new side channel attacks flaws found, they are quickly fixed. If you decide to write your own implementation, you must be very careful to not introduce these type of flaws. And in fact, your hmac.py solution from the previous homework is vulnerable to this type of timing attack. Why? Because it uses this non-constant time string comparison when verifying whether the calculated MAC matches the untrusted MAC value received from a possible attacker. So if you integrate your hmac.py in some network service where anyone can submit a message and the corresponding MAC, and your script will return the result of whether the MAC verification was successful or not, the attacker can measure this timing information and recover the MAC you calculated on your side by observing this timing information and adjusting the forged MAC until the MAC value you expect is recovered, which is pretty bad. The correct way to compare MAC is to use this compare digest method from the HMAC module that will perform comparison in constant time. So your solutions developed in this course will not be secure against timing attacks. Therefore, take this very seriously when you decide to use some of the code from your homework tasks in production systems. The whole conclusion here is that you have to be very careful when implementing your own crypto. The side channel attacks go far beyond timing attacks, which you see here in this example. Instead of timing information, the attacker could also learn secrets by measuring the power consumption, electromagnetic emission, or even sound emitted by the device that processes secret information. You may have heard of an attack where an electromagnetic emission produced by LCD screens can be captured meters away from the screen using a $20 radio receiver, as you see here. Or another attack where by measuring electromagnetic waves emitted by a smartphone, it is possible to recover the secret data processed inside the device. Here you can see such an attack in action. The customer-grade electronics we all use usually do not implement shielding or any other measures to prevent this type of leakage. The military-grade equipment is usually designed and certified to ensure that these type of attacks are prevented. And by the way, the side channel leakage does not apply only to technology. It is present whenever it is possible to infer some secret information from public information. Now, for example, a number of persons residing in a military base may be classified information that should not be disclosed, right? However, by looking at a public procurement specification, which lists how many pairs of boots should be delivered to the military base, we can also infer how many persons are likely residing there, right? And so on. I hope you got the point. But okay, enough for this lecture. Good luck with the homework.